Why don't airplanes fly on gasoline? At first glance, the question seems strange, since gasoline is the most common fuel. We use it every day. It is affordable, efficient, and works well in cars. It would seem logical to assume that aviation uses the same fuel, just in larger volumes. But reality is quite different. Modern airplanes are fueled with kerosene. And this is not a coincidence, but the result of strict engineering calculations. This creates a paradox. Gasoline is indeed well suited for engines on the ground. It evaporates easily and ignites quickly, making it effective in car conditions. It would seem like the ideal candidate. But it is precisely these properties that make it problematic in the sky. What works well on the road becomes dangerous at an altitude of 10 kilometers. If we explain the difference as simply as possible, the issue is not just about fuel power. More importantly, how it behaves under different conditions. An airplane is not a car. It operates at low pressure, in extreme cold, and must maintain stability for many hours without stopping. Under these conditions, fuel must be predictable. It should not evaporate too quickly, it should not ignite easily from random factors, and it should not change its properties during the flight. This is where kerosene proves to be much more suitable. To understand why, we need to briefly look at where kerosene even comes from. Kerosene is one of the fractions of oil. When crude oil is heated at a refinery, it separates into different parts based on boiling temperature. The lightest components turn into gas and gasoline, the heavier ones into diesel and fuel oil. Kerosene is somewhere in the middle. After separation, it undergoes additional purification, impurities are removed, special additives are added to prevent it from freezing or damaging system components. Only then does it become aviation fuel. Now let's return to gasoline and its main problem, volatility. Gasoline evaporates very easily. On Earth, this is an advantage. It quickly mixes with air and burns efficiently. But at high altitudes, the situation changes. Air pressure is significantly lower there, and gasoline begins to evaporate even more actively. Gas bubbles can form in the fuel system. This phenomenon is called vapor lock. Imagine a straw through which you drink water. If air bubbles appear inside, the flow will start to break or stop altogether. In an airplane engine, this is unacceptable. Fuel must flow continuously. If the supply is disrupted, the engine can stall. Gasoline evaporates faster, ignites more easily, and is better suited for compact engines with frequent load changes, such as in cars. But it is precisely these properties that make it unstable under low-pressure conditions and at high altitudes. Kerosene, on the other hand, is less volatile, more predictable, and more resistant to extreme temperatures. It is safer to store, more stable during delivery, and better withstands long periods of operation without interruption. It is no less effective as a fuel, it is simply better suited to specific conditions. Now let's consider the scale. A modern airplane is not just engines and wings. It is a huge system designed to transport hundreds of people or dozens of tons of cargo over thousands of kilometers. This requires colossal amounts of energy. Large passenger jets can carry up to 150,000 to 180,000 liters of fuel. During a long flight, for example, across an ocean, consumption can reach 80 to 100 tons. This means that a significant portion of the airplane's mass at takeoff is fuel. And here, the importance of its properties becomes clear. It must not only be efficient but also safe in such quantities. This brings us to today's reality. The price of aviation fuel directly depends on the cost of oil on the global market. And oil prices, in turn, are sensitive to many factors: geopolitics, conflicts, supply restrictions, decisions by exporting countries, and demand from various industries. Any major change in the world almost immediately affects the cost of kerosene. And since aviation consumes it in enormous quantities, even a small price increase translates into millions of additional costs for airlines. We see the consequences of this rather quickly. When fuel becomes more expensive, airlines' costs rise. To compensate, they are forced to increase ticket prices or optimize routes. This affects not only passengers but also cargo transportation. Shipping goods becomes more expensive, which indirectly impacts store prices. Ultimately, the choice of fuel for airplanes is not just an engineering question but part of a global economic system where everything is interconnected. At present, the average price of aviation kerosene is about 50 to 70 cents per liter. However, recently it has risen noticeably, especially in the US, where it nearly doubled in a short period. This is linked to rising oil prices and unstable global conditions. Meanwhile, airplanes keep flying, but airlines have to adapt, reducing flights, optimizing routes, and raising ticket prices. As a result, passengers feel this directly, flights become more expensive, and the choice of routes gradually shrinks. In Russia, a special aviation fuel standard, TS1, is used, kerosene specifically adapted for flight conditions, considering low temperatures and engine performance requirements. For international flights, Jet A1 standard fuel is also used. Despite differences in labeling, the principle remains the same. It is highly refined kerosene with defined characteristics that ensure safe and stable operation of aircraft. I believe that the choice of kerosene for aviation is not a coincidence or a compromise but the result of precise calculation. In conditions where stability, safety, and the ability to operate under extreme temperatures and loads are critical, kerosene is simply the best solution for the job. As long as physics and flight conditions remain as we know them, kerosene remains the most logical and effective choice for the skies.